In a balanced three-phase circuit, the currents in each phase are equal in magnitude and separated by 120 electrical degrees. This balance ensures that the net current flowing through the neutral wire is zero. When the loads on a three-phase circuit are unbalanced, the currents in each phase will no longer be equal. This imbalance can lead to a non-zero current flowing through the neutral wire. The neutral wire is designed to carry a small amount of unbalanced current. However, if the unbalanced current becomes too large, it can overheat and potentially burn through the neutral wire. To prevent neutral overheating, it is crucial to distribute the load evenly across all three phases. This can be achieved by connecting single-phase loads to different phases or by using three-phase loads that draw current from all three phases. Consider an example where two phases are connected to a neutral along with one B or C phase. The load will be unbalanced. The total current flowing through the two phases will be twice that of the current flowing through the B or C phase. This imbalance will cause a non-zero current to flow through the neutral, potentially leading to overheating. Three-phase circuits involving a neutral must be balanced to prevent neutral overheating. Unbalanced loads can create a non-zero current in the neutral wire, which can lead to its failure. Proper load distribution and careful consideration of the neutral wire's capacity are essential for the safe and reliable operation of three-phase circuits. Understanding the principles of balanced and unbalanced three-phase circuits is crucial for electrical engineers and technicians to ensure safe and efficient power distribution. Firstly, let's define a balanced three-phase system. A balanced system is one where the three voltages are equal in magnitude and are 120 electrical degrees apart. Secondly, a balanced load is one where each of the three phases has the same impedance. When both the source and the load are balanced, the neutral current is ideally zero. However, in real-world applications, perfectly balanced conditions are rare. Unbalanced loads are a common occurrence, leading to current flow in the neutral wire. This neutral current can cause several problems, including increased losses, voltage drops, and potential overheating of the neutral conductor. To mitigate these issues, it is essential to understand the factors that contribute to unbalanced loads and implement strategies to minimize their impact. Thirdly, load imbalances can arise from various sources. One common source is the connection of single-phase loads to a three-phase system. For example, lighting circuits, receptacles, and small appliances are typically single-phase loads. If these loads are not distributed evenly across the three phases, it can create a significant imbalance. Another source of imbalance is the presence of large single-phase loads, such as motors or heating elements connected to one phase. These loads can draw a substantial amount of current, causing a significant voltage drop on that phase and creating an imbalance. Fourthly, the impedance of the distribution system itself can also contribute to load imbalances. If the impedance of one phase is significantly different from the others, it can cause unequal current flow even if the loads are nominally balanced. This can occur due to variations in conductor size, length, or connections. To minimize the impact of unbalanced loads, several strategies can be employed. One approach is to carefully distribute single-phase loads across the three phases. This can be achieved by using a load balancing schedule, which assigns different circuits to different phases in a way that minimizes the overall imbalance. Another approach is to use three-phase loads whenever possible. Three-phase loads, such as three-phase motors and transformers, draw current equally from all three phases, helping to maintain balance. Fifthly, the size of the neutral conductor is also an important consideration. The neutral conductor should be sized to carry the maximum anticipated unbalanced current. If the neutral conductor is too small, it can overheat and potentially cause a fire. The National Electrical Code, or NEC, provides guidelines for sizing neutral conductors based on the expected unbalanced load. Sixthly, voltage regulation is another important factor to consider. Unbalanced loads can cause voltage drops on the heavily loaded phases, which can affect the performance of sensitive equipment. To improve voltage regulation, it may be necessary to use voltage regulators or automatic tap-changing transformers. These devices can compensate for voltage fluctuations and maintain a stable voltage supply. Seventhly, power quality monitoring can be used to detect and diagnose load imbalances. Power quality monitors can measure the current and voltage on each phase and calculate the degree of imbalance. This information can be used to identify the sources of imbalance and implement corrective measures. Eighthly, harmonic currents can also contribute to neutral current. Harmonic currents are caused by nonlinear loads such as electronic devices and switching power supplies. These currents can flow in the neutral conductor and cause overheating. To mitigate the effects of harmonic currents, harmonic filters can be used. These filters can reduce the amplitude of the harmonic currents, preventing them from flowing in the neutral conductor. Ninthly, in some cases, it may be necessary to use a dedicated neutral conductor for each phase. This is particularly important in systems with high levels of harmonic currents or unbalanced loads. A dedicated neutral conductor can provide a low impedance path for the neutral current, reducing voltage drops and preventing overheating. Tenthly, regular inspections and maintenance are essential for ensuring the safe and reliable operation of three-phase systems. Inspections should include checking for loose connections, damaged conductors, and overloaded circuits. Maintenance should include cleaning equipment, tightening connections, and replacing worn or damaged components. In conclusion, understanding the principles of balanced and unbalanced three-phase circuits is crucial for electrical engineers and technicians to ensure safe and efficient power distribution. By carefully distributing loads, using three-phase equipment, sizing neutral conductors appropriately, and monitoring power quality, it is possible to minimize the impact of unbalanced loads and maintain a reliable power supply. It is also vital to note that the NEC provides specific guidelines for sizing neutral conductors in various situations. For example, NEC Section 220.61 addresses the sizing of neutral conductors for household electric ranges and clothes dryers. This section allows for a demand factor of 70% to be applied to the neutral load calculation, recognizing that these appliances are not typically used simultaneously at their maximum rated current. NEC Section 310.15 addresses the ampacity of conductors in general, including neutral conductors. This section provides tables and formulas for determining the allowable ampacity of conductors based on their size, insulation type, and ambient temperature. It is important to consult the NEC for the specific requirements that apply to a given installation. In addition to the NEC, other standards and guidelines may also be relevant. For example, IEEE Standard 519 provides recommendations for harmonic control in electrical power systems. This standard sets limits on the amount of harmonic current that can be injected into the power system. Understanding and complying with these standards and guidelines is essential for ensuring the safe and reliable operation of three-phase systems. Furthermore, when dealing with three-phase power systems, it's essential to understand different wiring configurations, such as Y and delta connections. In a Y-connected system, the neutral wire is connected to the center point of the Y, which is typically grounded. The neutral wire provides a return path for unbalanced currents, ensuring that the phase voltages remain stable. In a delta-connected system, there is no neutral wire. Instead, the three phases are connected in a closed loop, forming a triangle. Delta-connected systems are often used in industrial applications where a high degree of reliability is required. However, they are more susceptible to voltage imbalances and harmonic currents. The choice between Y and delta connections depends on the specific application and the requirements for voltage stability, harmonic control, and reliability. In addition to wiring configurations, it's also important to understand different types of three-phase loads. Linear loads, such as resistors and inductors, draw current that is proportional to the voltage. Nonlinear loads, such as electronic devices and switching power supplies, draw current that is not proportional to the voltage. Nonlinear loads generate harmonic currents, which can cause problems such as overheating, voltage distortion, and equipment malfunction. To mitigate the effects of harmonic currents, harmonic filters can be used. These filters can reduce the amplitude of the harmonic currents, preventing them from flowing in the power system. There are two main types of harmonic filters: passive filters and active filters. Passive filters consist of capacitors and inductors that are tuned to specific harmonic frequencies. Active filters use electronic components to inject currents that cancel out the harmonic currents. The choice between passive and active filters depends on the specific application and the requirements for performance and cost. In summary, understanding the principles of balanced and unbalanced three-phase circuits, as well as wiring configurations, load types, and harmonic control techniques is crucial for electrical engineers and technicians to ensure safe and efficient power distribution. By carefully considering these factors, it is possible to design and operate three-phase systems that provide reliable power to a wide range of applications. It is also important to remember that electrical safety is paramount when working with three-phase power systems. Always follow proper safety procedures, wear appropriate personal protective equipment, and energize equipment before performing any work. By adhering to these safety precautions, it is possible to minimize the risk of electrical shock and other hazards. Additionally, consider the impact of power factor on three-phase systems. Power factor is the ratio of real power to apparent power. A low power factor indicates that a large portion of the current is reactive, meaning it does not contribute to doing useful work. Low power factor can lead to increased losses, voltage drops, and reduced equipment capacity. To improve power factor correction capacitors can be used. These capacitors supply reactive power to the system, reducing the amount of reactive current that must be supplied by the utility. Improving power factor can result in significant cost savings and improved system performance. Furthermore, it's crucial to understand the role of grounding in three-phase systems. Grounding provides a low impedance path for fault currents, allowing protective devices to quickly clear faults and prevent electrical shock hazards. There are several different types of grounding systems, including solid grounding, resistance grounding, and impedance grounding. The choice of grounding system depends on the specific application and the requirements for safety and reliability. Solid grounding provides the lowest impedance path for fault currents, but it can also result in high fault currents that can damage equipment. Resistance grounding limits the fault current to a safe level, but it can also make it more difficult to detect ground faults. Impedance grounding uses an impedance to limit the fault current and provide a means of detecting ground faults. The NEC provides specific guidelines for grounding three-phase systems. These guidelines specify the size and type of grounding conductors, as well as the location of grounding electrodes. Adhering to these guidelines is essential for ensuring the safety and reliability of three-phase systems. In addition to grounding, surge protection is also important for protecting three-phase systems from voltage transients caused by lightning strikes, switching operations, and other disturbances. Surge protective devices, or SPDs, can be installed at various points in the system to divert surge currents to ground, preventing damage to equipment. SPD are typically rated in terms of their surge current capacity, which is the maximum amount of current that they can safely divert. It is important to select SPD with a surge current capacity that is appropriate for the expected surge levels. The NEC provides guidelines for selecting and installing SPD. These guidelines specify the location of SPD, as well as the minimum surge current capacity. Finally, consider the importance of proper documentation and labeling in three-phase systems. All equipment should be clearly labeled with its voltage, current, and power ratings. Wiring diagrams and schematics should be readily available to facilitate troubleshooting and maintenance. Proper documentation and labeling can help to prevent errors and ensure the safety of personnel working on the system. Remember that continuous learning and professional development are essential for staying up to date with the latest technologies and best practices in three-phase power systems. Attend training courses, read technical publications, and participate in industry events to expand your knowledge and skills. By staying informed and engaged, you can ensure that you are providing the best possible service to your clients and customers. Proper load balancing is essential for three-phase power distribution systems to ensure efficiency, reliability, and safety. Imbalances in the load can lead to several adverse effects, including increased neutral current, voltage imbalances, overheating of equipment, and reduced system capacity. To mitigate these issues, electrical engineers and technicians must carefully consider load distribution and implement strategies to minimize imbalances. One of the primary causes of load imbalances is the connection of single-phase loads to a three-phase system. Single-phase loads, such as lighting circuits, receptacles, and small appliances, draw current from only one phase of the system. If these loads are not distributed evenly across the three phases, it can create a significant imbalance. For example, if a large number of single-phase loads are connected to phase A, while phases B and C have relatively few loads, phase A will experience a higher current draw than the other two phases. This imbalance can cause a voltage drop on phase A, as well as an increased current flow in the neutral conductor. To address this issue, electrical engineers often use load balancing schedules. A load balancing schedule is a plan that assigns different single-phase circuits to different phases in a way that minimizes the overall imbalance. The schedule typically takes into account the expected current draw of each circuit, as well as the diversity factor, which is the probability that all of the loads on a given circuit will be operating simultaneously. By carefully distributing the loads across the three phases, it is possible to reduce the neutral current and improve the voltage balance. Another strategy for minimizing load imbalances is to use three-phase loads whenever possible. Three-phase loads, such as three-phase motors and transformers, draw current equally from all three phases, helping to maintain balance. Three-phase motors are commonly used in industrial applications to power large equipment, such as pumps, fans, and compressors. Three-phase transformers are used to step up or step down the voltage in three-phase power systems. By using three-phase loads instead of single-phase loads, it is possible to reduce the overall load imbalance and improve system performance. In some cases, it may be necessary to use specialized equipment to correct load imbalances. For example, a static VAR compensator, or SVC, is a device that can inject or absorb reactive power into the system to maintain voltage stability and reduce load imbalances. SVC are typically used in large industrial facilities or power plants where there are significant load fluctuations or imbalances. Another type of equipment that can be used to correct load imbalances is a dynamic voltage restorer, or DVR. A DVR is a device that can inject voltage into the system to compensate for voltage spikes or swells caused by load imbalances or faults. DVR are typically used in sensitive applications where voltage disturbances can cause equipment malfunction or process disruptions. In addition to these strategies, it is also important to consider the size of the neutral conductor when designing a three-phase power system. The neutral conductor must be sized to carry the maximum anticipated unbalanced current. If the neutral conductor is too small, it can overheat and potentially cause a fire. The NEC provides guidelines for sizing neutral conductors based on the expected unbalanced load. It is important to consult the NEC for the specific requirements that apply to a given installation. Furthermore, it's crucial to regularly monitor the load balance in three-phase power systems. Load monitoring can be done using a variety of instruments such as ammeters, voltmeters, and power quality analyzers. By monitoring the current and voltage on each phase, it is possible to detect load imbalances and identify the sources of the imbalances. This information can be used to implement corrective measures and prevent potential problems. In conclusion, proper load balancing is essential for three-phase power distribution systems. By carefully distributing single-phase loads, using three-phase loads whenever possible, considering the size of the neutral conductor, and regularly monitoring the load balance, it is possible to minimize imbalances and ensure the safe, reliable, and efficient operation of three-phase power systems.